Hello everybody, this is Mr. Hinnon for this Institute Virtual Lab. In this one we're going to look at simple harmonic motion, and basically what we're going to be doing is we're going to be looking at a spring here. So we have a spring with some mass at the bottom and it's going to be bouncing up and down. So let's see if I can adjust this so you can kind of see all the motion there. So it's going to be bouncing up and down. That's going to put it in simple harmonic motion. So it's going to be in simple vertical kind of bounce. Now I want to make sure it doesn't go too crazy, so we're going to try to make sure it doesn't swing or anything like that. I want it to just go straight up and down. Then down here, what I have on the floor underneath it is I have a motion detector. That motion detector is going to detect how far it is from the bottom up to the bottom of that. Then on the computer over here, what I have is I have two graphs. One is a position versus time graph, and one is a velocity versus time graph. Those are going to allow me to actually find what we have going on. So that's what we're going to start off with. So I'm going to kind of show this going on, and you're going to hear this kind of in real time. So I have a 50-gram mass hanger on here with 20 grams on it, and then a 1.5 gram card. So the total mass on here is 71.5 grams. Okay, 71.5 grams. We want to change that to kilograms. I'm using the loose spring. The loose spring has a spring constant of 1.75 newtons per meter. 1.75 newtons per meter. So I have the spring constant. I know how much mass is hanging on it. Then I'm ready to actually collect my data. So I'm going to start this up, get it bouncing up and down like so. I'm going to hit the collect button. Collecting that data. And that's pretty much it. What I'm going to do over here is I wanted you to kind of see the graph. So I'm going to modify the graph a little bit. I'm going to come up here and I'm going to hit this auto scale button so you can see the graph spread out a little bit more. What you will see is you have these nice up and down kind of motions to the graph. That eventually what we're going to look at is we're going to look at simple harmonic motion in terms of sine waves and cosines and how we find the frequency. We're actually going to find the spring constant that way. But for right now, what we're going to be doing is we're going to highlight this data. We're going to come up here, we're going to hit the 1-2 stat button. That's going to give me statistics on my position graph. I'm going to do the same thing on my velocity graph, highlight my data, hit the 1-2 statistics button. And then since these are going to be really small, I'm going to make them a little bit bigger. So now we can see that data table. See this one. So we can see the general motion of the graph, but we can also see the data. We're going to be using some of the data in here to calculate some stuff. We're going to see how the elastic potential energy is related to the kinetic energy. If I look at my bouncing mass here, what I should realize is when it's up at its highest point, when it's at its highest point or lowest point, it's momentarily changing direction. So its velocity should be 0 at those points. But right as it's passing through the center of its motion, that's when it's moving the fastest. So we're going to compare the elastic energy it has at the top and the bottom with its kinetic energy going through the center. Because basically all we have happening here is we have elastic energy turning into kinetic energy. Elastic, kinetic, elastic, kinetic, elastic, kinetic, and over again. That has been our virtual Elastic Potential Energy Simple Harmonic Motion Lab. Hope you enjoyed.